All right, welcome to Tolleson Physics. So now what we're going to do is we're going to look at how fast you would have to drive to leave a hill, right? So you can approximate the curvature at the point where you're going to leave the hill. And so what we're going to do is we're going to do a problem where we can solve that. And so what I've drawn here is just a round hill. And we're going to try to predict at the very top of the hill what is the minimum speed you need to do to leave the hill. Okay, so let's think about that force diagram once that's focused. So let's think about the force diagram about this. So once again, force diagram for this object is we have a force due to gravity that's pointing down, and force due to gravity is mass times the acceleration of Earth's gravity, and then it has a normal force. And I'm going to draw the normal force smaller because we're on a hill. Now, let's think about what it means to leave the hill. So if you're leaving the hill, there is no normal force, right? So this normal force actually goes to zero, and this kind of goes away. What is this a force diagram for? It's a projectile. All right, so we're going to use that. So what we're saying from this force diagram is really the net force when you leave the surface of the Earth is just the force due to gravity, which equals mg. Okay, well, so how are we going to apply that to the question that we have? So we have this question about how fast do I need to go to launch off of there? Well, don't forget that the net force, when you're dealing with circular motion, is related to the mass times the velocity squared over the radius of the hill. And so that's a net force. This is a net force. So I can set them equal to each other. It's the same net force. And so it turns out I don't need mass. Mass cancels. So it doesn't matter how large this vehicle is. If I can achieve the right speed, it's going to launch. All right, so this simplifies to v squared over r equals g. And then let's cross multiply and hit it with the square root. And so r times g square root. All right, and so this actually tells me how fast I need to go to leave this hill. All right, let's do one more example. So the other example that I wanted to do was in a loop-de-loop. So a loop-de-loop, they're not perfect circles. There's reasons for that. But in a loop-de-loop, there's still a curvature at the top. And so there's still a radius for that part of the circle. All right, so there's still a radius for that part of the circle, even though the radius is changing. So you can actually use circular motion on things that are not perfect circles. As long as we know what the curvature is at the point we're talking about. So then let's think about what the force diagram is at the top. I didn't leave enough room to draw it. So what I'm going to have is I'm going to have the force due to gravity pulling it down, and then remember the track pushes against the roller coaster, forcing it to turn in a downward direction. So the normal force is 0. So the question I actually want to ask about this is what's the minimum speed that I need to prevent myself from falling off of this loop-de-loop? And so we're going to do it in a very similar way. We're going to go ahead and say, okay, if I fall, the boundary condition is just when I hit a normal force of 0. So once again, I end up with a projectile. I end up with this very similar thing that we just saw, right? The net force is equal to the force due to gravity, which is mass times g. Wow, this does not want to focus today. Okay, and then I can use the other part of this, right? The net force due to traveling in a circle is the mass times the velocity squared over r. Well, that's interesting. I'm going to get basically a similar result, right? It's the same setup as before, even though it looks like a different situation. And so since we've done it before, I can just write it And actually, I usually write GR instead of RG. It just looks right to me. Whatever. But when I simplify that, so it actually turns out I get a similar solution for a loop-de-loop that I did for a hill. You know, it's this idea that when the normal force becomes 0, then I'm going to not have a normal. Nothing's pushing against me any longer, and I'm going to leave that that surface. So those are a couple of examples using roller coasters specifically, but we can apply this to a whole bunch of other things like cars going around curves, you know, the little spinny rides where you're stuck up against the wall and you don't fall down and the floor falls out from you. So there's a number of other situations that we'll be looking at as we go through our problem sets.